In this video, we're discussing curvature, which is denoted by a Greek letter kappa. It looks like a K. We can think of this as a function of length or distance traveled along the curve, or we can think of it as a function of time, depending on whether our curve is parameterized by time or length along the curve. So this depends on S or T. Maybe our curve looks like this. Let's say that's our curve. Now, curvature is a measure of the sharpness of the curve. I think of it as a measure of how curvy the curve is. That's not technically, that doesn't technically mean much, but I can see over here it's not very curvy, over here it's curvier, and that's the curviest part of this curve. So let's plot a couple of points and think about what this means. So I'm trying to measure how much my curve is turning, like how sharply it's turning. And let's say I want to measure that at this point A and this point B and this point C. One way I can do that is by looking at how much the unit tangent changes in the vicinity of that point. So the unit tangent vector, that's t hat, remember it's 1 unit long, and it points in the direction of motion. So if we're going this way, it's going to point in that direction. So near A, here is my unit tangent, and here is my next unit tangent. And we've got infinitely many unit tangents. Now all of them have exactly the same length, and they're all headed in the same direction. So even though they have different initial points, if I were to draw them all with their initial point at the origin, they would all look exactly the same. So here the curvature at A, or here the curve isn't curving at all, so the curvature at A is 0. And that's because we've got a straight line over here. Now if I want to compare the curvature at B and C, I can look at unit tangent vectors in the vicinity of both of those points. So here's a unit tangent vector near B, and there's the next one, and there's the next one, and then the one at B looks like this, and then we've got the one after that looks like that, and the one after that looks like that. So those unit tangents are changing there. Now let's think about the unit tangents near C. There's one, there's one, there's one. Do you see how they're changing direction extremely fast? Or they're changing direction a lot as we move a little bit along the length of the curve. That means the curvature here is larger than the curvature here, because these vectors are changing a lot faster than these vectors are changing. Or I'm saying faster as if we're parameterizing this curve with t, but it's really about how this changes as the arc length changes, as we move along the length of the curve. It really doesn't have anything to do with time or how fast we're going. So if I'm classifying these points A, B, and C from least curvature to greatest curvature. The one with the largest curvature is the point C. The curvature at C is the largest. Curvature at B is smaller than that, and curvature at A is 0. That's as small as it can get. Curvature is always positive or possibly 0 if the curve isn't curving at all. Okay. Now another way to get the curvature intuitively is to draw what's called an oscillating circle. An oscillating circle has the same curvature as the curve at that point. So a circle has a constant curvature. If we've got a circle, I'm trying to draw a circle, perfect circle, and its radius is r, the curvature of that circle is defined to be 1 over r. So if my circle is very small, that r is very small, 1 over the curvature is going to be very large. If my circle is larger, the curvature is smaller. So if this was a 3, my curvature, if my radius was 3, my curvature would be 1/3. My radius is 1, my curvature is 1. 1 is clearly larger than 1/3, so this one would have a larger curvature than this one. And I think intuitively we know that's true. Like, this is curving a lot more, a lot faster than this one is. And if I made an even larger circle, this is going to feel much flatter if I was traveling along the curve than if I was traveling along this curve. So these 3 circles, I'm going to call this one R1, this one R2, and this one R3. The one with the smallest radius has the largest curvature. So I'm going to label these 3 circles. This is circle number 1. This is circle number 2. And this is circle number 3. And curvature is largest when the radius is smallest. So the curvature, I'm going from least curvature to greatest curvature. And I'm classifying these 3 circles. The one with the largest radius has the smallest curvature. Because this, oops, I wrote r cubed. It's r sub 3. The curvature for this circle number 3 is 1 over r3, and that radius is largest, so 1 over that is going to be smallest. Now here, this radius is next, and then this radius. Actually, let me write it a little differently. Let's just write the radii in order. R1 is less than R2, which is less than R3. Like, this could be like 2, 3, and 4, right? This one is smaller than this one, and this one is smaller than this one. Now, if I take reciprocals of that, those inequalities flip. And I think the easiest way to see that is to think about 2 versus 3, and then 1/2 versus 1/3. 2 is smaller than 3. Now if I take 1 and I divide it into 2 pieces, each of those pieces is larger than if I take 1 and divide it into 3 pieces. So whenever we take reciprocals, the inequality flips. So this is how our radii are ranked from smallest to largest. If we take reciprocals, we get this. And this is the curvature of the first circle, or the smallest circle, and that's greater than the curvature of that medium-sized circle, which is greater than the curvature of the largest circle. Okay, so intuitively that's what's going on. Now, what we were doing here was we were trying to find a way to measure this curvature by looking at the change in the unit tangent vector. And that's exactly how our curvature is defined. So let's write that down. Our first definition of curvature, the way we're measuring how sharp our curve is for a given value of the arc length parameter s, is the magnitude of the derivative of the unit tangent vector with respect to s. So that's our first definition, or it's really just our true definition. It's how we're defining it. But we don't tend to use this formula. using this formula requires finding the arc length parameter, parameterizing the position in terms of arc length, then finding the unit tangent, then taking its derivative with respect to s. That's a lot of work. So we don't tend to use this. Most of the time we're working with r as a function of t. So we have position as a function of time. So with that in mind, I might want to find my curvature in terms of a different variable, t. Well, I know by the chain rule, that the derivative of the unit tangent with respect to t is the derivative of the unit tangent with respect to s, so the arc length parameter, times the derivative of the arc length parameter with respect to t. So this is the change in the unit tangent as we go along the length of the curve, like we were doing in this picture over here on the other side of the paper, times the speed. So this is how much the unit tangent changes with respect to length times the instantaneous change in length or distance traveled along the curve per unit time. So if this is a change in a vector per meter and this is a meter per second, the meters cancel and I just get a change in a vector per second. So that is the chain rule. It's derivative of the outside evaluated at the inside, which is the arc length parameter, times the derivative of the inside. Well, we talked about this last time. This is the derivative of length with respect to time, or the derivative of distance traveled along the curve with respect to time is speed. So I'm going to write this using prime notation instead. Oops, I don't need magnitudes yet, but I'm going to need them in a minute. Let's take magnitudes of everything. The magnitude of this, and this is not a dot product, that is a scalar function of t times a vector. So I've got that. And the magnitude of a vector function times a scalar function is just the magnitude of the vector function times the magnitude or the absolute value of the scalar function. And ds dt, that's change in distance per unit time and it's instantaneous, that's another name for speed. So you could call that v of t if you want to, or you can call it r prime of t, same thing. Because velocity is the derivative of position, right? So this all just comes from the chain rule. Now, the derivative of t hat with respect to the arc length parameter, that right there is the definition of curvature. So that's curvature right here. If I want to get curvature by itself, I just divide both sides by this guy. So now I've got curvature as a function of time. It's this divided by that. Or if you prefer, you could call that t hat prime divided by speed. That'd be fine too. So this is one way that we calculate curvature. This is a much more direct way. If you have r of t, you find its derivative and you find the magnitude of the derivative, so that's speed. You find t hat, you often have to find that anyway. You find its derivative and you find its magnitude, and then you divide those to get the curvature. So if I have to go to the trouble of finding the unit tangent and finding the speed anyway, this is a really good formula to use. Now, in this video, I'm going to go through and I'm going to derive various formulas for curvature. All of them are equivalent, and you can use whichever one you want, whichever one's most convenient. So I would say use this one. When you need the velocity and t hat prime anyway. T hat or t hat prime. So if I've already gone to the trouble of calculating this because that's what was required of the problem, I might as well just go ahead and compute this. It's really not that difficult to compute this guy. So that's the definition. I almost never use this, but it is a good formula for interpretation. Curvature is defined to be the magnitude of the change in the unit tangent as we move along the curve, and it's instantaneous. So as we look at this, as we move along the curve, the unit tangent's not changing a lot here, it is changing a lot here, it's not changing at all there. So this is the smallest curvature, medium curvature, or excuse me, smallest curvature, medium curvature, and largest curvature, because it's changing the most right there. Okay, so that's our second formula for curvature. The third formula for curvature can be derived using our formula for a sub n. Now, earlier in a different video, we proved that the tangent or the normal component of acceleration, or sometimes called the radial component of acceleration, is the speed squared times curvature. Okay, so if I want, from this, I can solve for curvature. Curvature is just a sub n divided by speed squared. Now we remember that it took a lot to get to a sub n, so I'm going to try to write a sub n in terms of other quantities that I'm accustomed to. So it's nice, it would be convenient to write a sub n in terms of acceleration, in terms of velocity, in terms of the derivatives of r prime, r double prime, and all of that. So we're going to do that. Now, we remember that if our acceleration vector looks like this, it has a component in the normal direction. Maybe this is our curve. It has a component in the direction that we're turning, and it has a component in the direction that we're heading in. So if we're heading in this direction, there's my unit tangent, and my unit normal points in that other direction. It's at a 90-degree angle. Well, this side is defined to be the projection of A onto the unit tangent. It's the part of our acceleration vector that's parallel to the unit tangent vector. So that's a sub t times t hat, and we came up with formulas for that last time. And if I take that and I add that to a sub n times n hat, well, that gives me the acceleration vector back. So we know that this is true because of what we've discussed last time. The acceleration is some constant times the unit tangent plus some constant times the unit normal. And this constant tells us the acceleration in the direction that we're moving. And this constant tells us how much we're turning, how much of our acceleration is pulling us to turn in that direction of the unit normal. Okay, so now I know that a sub n is equal to this from our derivations last time, and I know that curvature, I can solve that for curvature, is equal to a sub n divided by the velocity, or the speed squared. So I'd like to find a sub n now in terms of velocity, acceleration, and so on, so that I can write the curvature formula in terms of velocity and acceleration. So what we'll do is draw a little angle theta there. Now, according to the Pythagorean theorem, the length of this side, that's a sub n, because remember a sub n is always non-negative, it's positive or zero. The length of this side, well, that's opposite theta. So a sub n, just from trig, has to be the magnitude of a times sine of theta. Now that looks a little bit like our cross product formula. Remember, with our cross product of u and v, we had the magnitude of u times the magnitude of v times the sine of the angle between them. Well, we can use that here. This is the angle between the acceleration vector and the unit tangent. So I'm going to multiply by the unit tangent and divide by the length of the unit tangent. But the length of the unit tangent is 1. So in the numerator, I just have the cross product, or excuse me, the magnitude of the cross product of A with the unit tangent. Now remember what the unit tangent is. The unit tangent is the direction that we're moving. So to find the unit tangent, I compute the velocity, and then I divide by the speed. So the velocity is telling me the direction and speed I'm going if I find its magnitude, and if I divide by the speed, well, that just makes it a vector that's 1 unit long that's heading in the right direction. Well, I've got the cross product now of 2 vectors, and this is just a scalar in the denominator. So it turns out that I can factor that scalar out from all of this, and we get something that looks like this. All right, so that is another formula for a sub n, and that is a sub n in terms of the acceleration and the velocity, and then the speed is in the denominator. So I can substitute this in right here, and I can get curvature in terms of acceleration and velocity. So my curvature is, as a function of t, it's a sub n, which is all of this, divided by the speed squared. Well, dividing by the speed squared is the same as multiplying by 1 over the speed squared. Dividing by a fraction is multiplying by the reciprocal, right? We're just going to take that and flip it. Or you can think of it as like dividing by 2 is the same as multiplying by 1/2, same thing. So I've got a sub n times 1 over the speed squared, and that gives us this. Curvature in terms of acceleration and velocity, or if you prefer, and this is the one I prefer, acceleration is r double prime, velocity is r prime, and that's r prime cubed down there. So I have used all these intermediate steps to get here. So both of these are alternate forms for curvature as a function of time. You might say, okay, when would I use this as opposed to this? Well, I might use this if no one asked me for t hat or t hat prime. If I have r, it's easy enough to find r prime and r double prime, take the cross product, find the magnitude, find r prime, find its magnitude, cube it, and divide. So that's curvature in terms of derivatives of r, which I think is really nice. Or if you're thinking in terms of the physics, we've got acceleration crossed with velocity as giving us, well, it's part of the acceleration that's acting perpendicular to the velocity. And then we have to divide by this velocity cubed in order to get curvature back. So, okay, now that's one formula for curvature. We've got 3 so far. We've got this one, and this one. Now this one simplifies a lot if our plane, or if our curve, excuse me, is in the plane. So let's say that we're in the plane. Now I can think of any curve in the plane that's parameterized by r of t as a curve in 3-dimensional space where the z component is just 0. That would be necessary in order for me to take this cross product. So let's say we're in the plane. This has components x of t and y of t. But because we're in the xy plane, z is equal to 0. Well, according to this formula, if I want to find the curvature, first I find r prime. Then I find r double prime. And then I take their cross product. So I've got x prime, y prime 0, and x double prime, y double prime 0. Okay, so we're going to keep going. R prime crossed R double prime is, cross out the row and column containing I hat, we get 0 minus 0. So that's 0 times I hat. Minus Cross out the row and column containing j hat, 0 minus 0, again. Plus, cross out the row and column containing k hat. We finally have something interesting. So I've got x prime times y double prime minus y prime times x double prime. So I've heard people call this a two-dimensional cross product. It's really not. It's a cross product in three-dimensional space. This is still perpendicular to the plane that contains the velocity and acceleration vectors, so it has to go out if your plane is in 3D, or your curve is in 2D. So this vector goes outside of the plane, that 2D plane that the curve is in. Oops, forgot my x double prime. But yes, and it makes sense. If this is in the plane and this is in the plane, the cross product is entirely in the z direction, and it has this magnitude. Now, according to this formula, I need the magnitude of that vector. Well, if it only has one component, this squared plus this squared plus this squared, take the square root, you're going to get this back, as long as it's positive. So we need the absolute value of that. If that's a 3, the length is 3. If that's a negative 3, the length is 3. Okay. And let's see, we also want r prime cubed in the denominator. So this is going to go in our numerator. And I need, it's not r prime cubed, excuse me, that doesn't make any sense. It's the magnitude of r prime cubed. Well, r prime looked like this. It had vectors, or it had components x prime, y prime, and 0. You take its magnitude. So you take the components, square them, add them, and take the square root, and then you cube it. Now when you cube this, you can actually write it two ways. You could write it this way, or it's just a property from algebra. If I have the square root of a cubed, that is a to the 1/2 cubed, or a to the 3/2. Excuse me, there we go. Now there are two ways of writing this. We can take the square root first and then cube it, and that's what I've got going right here. Or it's also legal if I cube it first and then take the square root. Most of the time, if I'm working with numbers, I want this one because it makes the numbers smaller and then I cube them. If I'm working with functions of t, it's convention to take that power and then put it on this expression inside the radical. So we're going to call this this. Or, if you prefer, x prime squared plus y prime squared to the 3/2. Alright, so that is the denominator of this guy. So we had earlier, curvature was the magnitude of r prime crossed with r double prime divided by the magnitude of r prime cubed. Now, according to this, if our curve is in the xy plane, we can think of that curve as being in the xy plane in three-dimensional space with just nothing happening in the z direction. This numerator simplifies to x prime y double prime minus y prime x double prime. Of course, you could put those in a different order because multiplication is commutative. You need to subtract in this order, though. You could just flip these if you wanted, or flip those if you wanted. And then this denominator is this, x prime squared plus y prime squared, and you raise all of that to the 3/2 power. So this is what we might use for curvature if we're in R2 where R has components x of t and y of t. Now our last formula for curvature, so this is our fourth, our last formula for curvature comes from looking at a curve in the xy plane and trying to find its curvature. If you have y as a function of x. Now to make things easier on myself, rather than thinking of y as a function of x, I'm going to think of y as a function of t, but it's the same thing. If we're talking about a curve in 2D, in R2, with an x component and a y component, or an independent variable and a dependent variable, that can be parameterized this way. If this was originally y equals f of x, I can let x equal t, and I'll let y equal f of t. This x-axis and the t-axis would be exactly the same thing because x is equal to t. So I let my x be t, I let my y be f of t, and I'm in the plane, but I need a third dimension so I can take that cross product because this vector, that cross product of the two actually extends out of the plane. It's going to point towards us like my pen is pointing at you right now. So that's 0. And if I apply this formula to this, I get another formula. So let's do that. We'll compute r prime and r double prime. And we need to compute the cross product now. This vector is 1 f prime of t and 0. This vector is 0 f double prime of t and 0. Taking the cross product, we cross out the row and column containing I hat, we get 0 minus 0. Then we cross out the row and column containing j hat, we get 0 minus 0. Then we cross out the row and column containing k hat, we get f double prime minus 0. So this is the vector with z component f double prime. So its magnitude is just the magnitude of f double prime. Whoops. Or absolute value of f double prime. And I think that makes sense. Remember what the second derivative represented in Calc 3, or excuse me, in Calc 1? Represented concavity. If we're changing from concave up to concave down, like this was our measure of it. And when this is 0, it's when we have that flat spot when we're going from concave down to concave up. So it makes sense to me that that would be related to curvature. Alright, so that's our numerator, and our denominator is r prime, and we find its magnitude and then we cube it. Here was r prime, so its magnitude is the square root of 1 squared plus f prime squared. So it's the square root of 1 plus f prime of t, quantity squared. And we have to cube that. So curvature is given by this f double prime divided by the square root of 1 plus f prime squared, and then you cube it. Or if you prefer, you could call that f double prime divided by the square, I keep doing the square root, sorry. If you prefer, if I take the square root of something and I raise it to the third power, that's raising that whole thing to the 2/3 power. I said that wrong. 3/2 power. Sorry about that. This power divided by that power. So that is our fifth and final formula for curvature. So you've got options. You've got lots of options for calculating curvature now. Let me write them all down, summarize. Remember, curvature is represented by kappa. It's a measure of the sharpness of the curve. I say informally, it's a measure of how curvy the curve is. And we define it to be the magnitude of the change in the unit tangent with respect to arc length. So if the unit tangent is changing a lot with respect to arc length, then we say the curvature is large. If it's not changing at all as we move along the length of the curve, then we say the curvature is 0. So that would be straight line motion. If there's any kind of curve at all, this is going to be positive. So this is the definition. We don't tend to use it. Then using the chain rule, we were able to prove that curvature can be written as a function of t this way. You take the magnitude of t hat prime and you divide by the magnitude of r prime. So that's one option. Then, using the definition of the normal component of acceleration, we were able to prove that curvature as a function of t is the acceleration, or the magnitude of the acceleration crossed with the velocity, divided by the speed cubed. Or if you prefer in terms of r, acceleration is r double prime. Velocity is r prime. And so I've got the magnitude of r prime cubed down here. So this is what I tend to use if my curve r is in 3D and it has components x of t, y of t, and z of t. So I use this in that case, or I also use this one. And I tend to use this one if I have to calculate the unit tangent. If I don't have to calculate the unit tangent, I would just as soon do this one. Because once I have t hat, it's not too difficult to take a derivative and find its magnitude. Even though, yeah, t hat can be pretty involved because of the magnitude in its denominator. So this is an option. This is also an option. Now, if you are in R2, so R has components x of t and y of t, I can think of that as a curve, a space curve, with a z component of 0. If I use this in this formula, I'm able to derive this version of the curvature formula. It was where did it go? X prime times y double prime minus x double prime times y prime. That's what our numerator simplifies to. And this, that's the magnitude of the velocity vector cubed, turns out to be x prime squared plus y prime squared to the 3/2 power. And then our last formula could also be called k of x. So if we're given y equals f of x or y equals f of t, and we're just dealing with this plane curve that's described this way, like Calc 1, Calc 2 style, then this simplifies to, or this numerator simplifies to just the magnitude of f double prime divided by 1 plus f prime squared. You take the square root and then you cube it. Or if you prefer, and I do prefer, I'm going to call that to the 3/2 power. Okay. So these are the 5 formulas. Never use the top one. And these are the conditions when you use them.